Welcome to the CAD/FIM ANSYS tutorials. This is Christoph Gebhardt, and I'd like to show you how to perform an electrical, thermal and structural analysis using ANSYS AIM. What we're dealing with is a fuse, and we want to study the current path, i.e. the voltage drop that occurs, the temperature that arises, and the deformation that arises due to thermal expansion. The whole thing has to be calculated in a manner that links everything together, i.e. all the physical properties, the electrical, the thermal, and the structural properties are put into a single analysis, because we're dealing with non-linear material behavior, as the material properties are temperature dependent. When we start ANSYS AIM, we immediately find ourselves in the simulation environment. We can see the workflow window down in this bottom area. The various operations are defined within this window. This can be done manually by compiling the individual steps in the process step by step, or by using predefined templates, which are available as typical analyses such as structural, fluid flow, thermal, and electrical analyses. In this case, we're going to use the template for electrical analysis. Next, we specify that this analysis is not simply going to be an electrical analysis, but rather a combined electrical, thermal, and structural analysis. AIM guides the user by providing a suggestion for the next step, marked blue, which in this case will be to create the simulation process. We're then asked to input the geometry. The simulation process is created and then processed to the extent to which this is possible at this point. The status of the remaining operations is indicated as follows: yellow, meaning something is still to be updated here, and red, meaning something still needs to be inputted. Let's take a look at the first operation, the yellow one. When it comes to the mesh, we can alter the mesh settings and then continue by accepting the predefined setup. Once the mesh has been created, we then further define the physical properties, and AIM directs us here so we can define the boundary conditions. Before doing that, we want to allocate a different material. By default, all components are defined as being made from steel. In this case, we want to ensure that the conductor is made of aluminium. So we select the geometry, assign it, and change the material from steel to aluminium. Once again, AIM directs us to the place where material is defined, so that we can assign a material to the two as yet undefined synthetic components. So we select these two parts and search for polyethylene in our material databank, and then assign this material to the parts. Nevertheless, we can here see a note to the effect that definition of the material properties is incomplete. We therefore go to where materials are defined and further define the properties and the electrical resistance. For the next step, AIM directs us to define the boundary conditions, and we firstly select the electric boundary conditions. We're going to be defining a current. Of 30 amps and a voltage of 0 volts. There are also some other boundary conditions that we're going to define. We want the thermal boundary condition, whereby we assume that the next component's contact points are guaranteed to a temperature of 30 degrees. We can define the structural boundary conditions in exactly the same way. We are defining a support, a fixed support, with respect to these contact points, and we are thereby ensuring that this component is held firm at these points. In order to once again check the boundary conditions, we can take a look at the list of boundary conditions, or we can see a graphic representation of the current, the voltage, the temperature, and the structural support. Additional features of the physics definition include, for example, the interfaces, the interaction between the different components, the contacts that is. We can see that there is firstly a contact between the two halves of the casing, then another between the rear casing and the conductor, and also between the front casing and the conductor. This definition of the contacts is now well underway, and we can continue to the next step, which is to perform the analysis. Once the analysis has been performed, we can visualize the predefined results, such as the electric potential, for example, or the current density. In order to add more results, you select the result variable, such as temperature, and the location, for example the rear casing and the conductor. And you'll see the temperature, which in this case is 44 degrees. Similarly, we can supplement the results by adding the displacement. We select the location, and we can then see the deformation. So you can see how ANSYS AIM is an intuitive and useful simulation environment that enables a wide variety of physical problems to be solved, either in isolation or in combination, and in a very straightforward manner.